Good afternoon, everyone. My name is Stuart Chambers, and today I'm going to be doing a presentation on the concept of generating lift and Bernoulli's principle. So over the past couple of weeks, we've studied a couple of different topics. In the previous week, mathematics and aging aircraft, and then this week we took it a step further by talking about physics and physics' effect on aging aircraft. So today I was going to do a presentation on a subject I found particularly interesting, the concept of physics, and that's Bernoulli's principle, and the concept of how Bernoulli's principle can be utilized to both generate lift, create flight. So let's go ahead and get started. So let's go ahead and talk about first, what is lift? Lift is the mechanical force generated by a solid object moving through a fluid. So in this case, we're going to treat fluid as the gas around the aircraft, or for instance, the air. So the pilot can control lift at any time. Anytime he moves the yoke or stick in any direction, fore or aft, the angle of attack is changed. The angle of attack is essentially the pitch at which the nose of the aircraft is at, so angles up or down. And that will change the angle of attack and the position of the wings, at which point you can generate lift. So how exactly is lift generated? And that's through thrust. Thrust is essentially the force moving the aircraft forward, and it can be, or basically described as the force exerted that is greater than drag pushing the aircraft forward. So according to the Pilot's Handbook for Aeronautical Knowledge, these basic concepts are what eventually allow us to generate flight. So now let's talk a little bit about potential energy as we move towards Bernoulli's principle. Potential energy is energy possessed by a body by virtue of itself or its position relative to others, stresses within itself, electric charge, and other factors. So essentially, potential energy is simply an aircraft that is stationary. Is the object by itself unmoving. Now, since we know that there's an object that is unmoving, thus storing and gaining potential energy, we can move towards kinetic energy, which is energy which a body possesses by virtue of being in motion. So, for instance, any time you're moving, playing a sport, we see the ball bouncing. Now, roller coaster energy in motion is kinetic energy. So now that we know potential energy and kinetic energy, we can move to apply it to Bernoulli's principle. Bernoulli's principle states that if energy is neither added nor taken away from a fluid in motion, any increase in its velocity will cause a corresponding decrease in its pressure. The velocity of moving fluid relates to its kinetic energy, and its pressure relates to its potential energy. So as we can see through the diagram on the right, there is an area of high pressure followed by a slow-moving fluid, or as described by V1. And then as it pushes through the venturi, which is essentially a condensed area within the tube, there is a decrease in internal pressure, however, a rapid increase in the fluid speed, and then, of course, as the pressure levels out again on the other side. So essentially, as you reduce there's a rapid decrease in pressure, there's a rapid increase in fluid speed. Now, that is just the basic of Bernoulli's principle, so how does this apply to aviation? Well, a practical application first would be to understand exactly just how it comes into play in everyday life. For instance, on the right, we have what may be either a can of spray paint or just a hose you would use for gardening, and you see as the atmospheric pressure pushes down on the liquid inside, you have a metal tube. The area of low pressure on the outside creates a differential, thus pushing the liquid up, and it goes through an atomizer in the top, which then, as the liquid meets with air, becomes a spray. So you can see here how Bernoulli's principle takes effect in just a simple everyday application. So for flight, how exactly does Bernoulli's principle work to generate lift? Well, as we talked about before with angle of attack, as the angle of the wing plus the thrust generated by the aircraft moves the aircraft forward, we generate this here, the longer path or equal transit theory, in which you have an upper streamline, which is the air passing over the top of the wing foil, and the lower streamline, which is passing under the bottom portion of the wing foil. As it passes through the bottom, you can see the design here creates an area of high pressure and low velocity, while the air passing over the top creates high velocity and low pressure, Bernoulli's principle. And what essentially happens as a high pressure attempts to meet with the low pressure, it forces the air upward, generating lift. So here we're not actually discussing the concept of how Bernoulli's principle generates thrust, but how it generates lift on the wings, which allows the aircraft to then create flight. As you can see from the GIF on the left here that I have. It's a basketball that has been rotated in a specific direction as to generate an area of high pressure underneath of it, and then an area of low pressure over top, essentially by its state of motion. And as it travels forward, it actually just doesn't drop straight down. It actually generates a small amount of lift, allowing it to travel forward. Now, like I said before, introducing angle of attack. You see here from the picture on the right, as we keep a standard 0-degree angle of attack, there's no or just a small portion of lift, as there's no distinct area of high pressure or low pressure being formed over the wing. And the Kanata effect is the tendency for fluid jet streams, in this case the air passing over the wing, to attach themselves to convex surfaces, the convex surface being the top of the wing foil. So here we see with no angle of attack, there's little to no lift. And then as we increase the angle of attack on the wing, approximately 10 to 20 degrees, we see a lift force being generated as high pressure forms underneath the wing and low pressure forms on top. So here we see the Kanata effect as the fluid jet streams here attach themselves to the convex surface. And then here, as we have a high angle of attack, almost 45 degrees, we see the effect, the Kanata effect, taking so even more, an area of extremely high pressure and very much so area of low pressure forming, and without a significant thrust to push the aircraft forward, you can generate a stall, which is a pockets of low pressure here formed by the Kanata effect, stalling the aircraft out. So we see here, as increasing angle of attack, we see the different forces acting upon Bernoulli's principle here over the wing and how that affects aircraft. So now let's try to apply it instead of just the concept of lift. How does Bernoulli's principle also apply to the development of jet engines? Well, if we look at the diagram here on the right, we'll see the different types of jet engines and exactly how the turbine works to generate thrust. So it's simple. Air taken in from the front of the engine is compressed 3 to 12 times its original pressure in the compressor. Fuel is added, air and burned in a combustion chamber to raise the temperature of the fluid mixture to a certain degree, resulting in hot air, and that's passed through the turbine, which drives the compressor. So these compression areas are essentially Bernoulli's principle at work. We're taking air from a high pressure area and forcing it into low pressure areas, rapidly moving it, compressing it, creating almost an explosive like force, high heat, and thus generating thrust out the rear chamber of the turbine engine. And this here, in combination, we can apply Bernoulli's principle to both this and the wing foil, and these two together are what allow us to both generate the thrust necessary for flight and the lift in order to get the airplane off the ground. So in total, some of the things that we've talked about are the basic concepts of lift. We've talked about kinetic and potential energy and how those are some of the basic factors that take part in Bernoulli's principle. Bernoulli's principle itself and how it works in the concept of lift and flight. So the area of highs and low pressures that help us generate lift on the wing foil, and how it creates thrust through the concept of the jet turbine engine. And what practical applications do Bernoulli's principle have? We took a look at maybe a potential use for how it works with spray cans and other things in everyday life. So overall, these are the references here. What I learned most about the physics in the past week is the concept of how these small concepts can apply to aging aircraft as well. For instance, if Bernoulli's principle with the concept of lift on the wings, if maintenance does not take proper care of those wings, or repairs are done incorrectly, if the angle of attack is increased too dramatically and so much stress is put on the wings, it can create a catastrophe. For instance, the stress could cause the wings to rupture, like in the Japan Airlines incident. It could cause if too much stress is put onto a damaged tailpiece, it can cause that to rupture and thus leading to a catastrophe. I hope everybody enjoyed this presentation. Thank you very much.